Well, good morning, dynamic students. Unfortunately, nobody has showed up yet, so we'll just be patient and wait. Today is December 2nd. Everything's backwards on my screen, so it looks like a 6, but it's December 2nd. The date on my screen looks like 0606, but it's really 2020. And we're going to study, I thought we'd go back over that ICZV business. I want to make sure you guys understand that. And the problem I picked out, a couple of problems here. One of them is 1687. And I guess I could draw that. You're supposed to draw things to scale. Did you know that? You're supposed to measure angles. So let me see if I can get that on the board, and then when you show my students show up, we can go through it. This is problem 1687. It's on page 370. Okay. So I need to draw a 1/2 meter to scale. Hey, we got a customer already. Alex is here. Good deal. Welcome, Alex. I wonder what would be a good scale for a 1/2 meter. 5 centimeters sounds pretty good. Yeah, let's do that. We'll put 5 centimeters here. That's pretty good. And then 4 centimeters going this way. Okay, we can do that. Hey, Taylor's here. Ashley's here. We got a good crowd. We got Alex, Taylor, and Ashley so far. We got a good class. Oops. I just pushed the wrong button, I think. Dang it. Well, we'll try again here. I think I just logged out somehow. I don't know what I did. Yeah, I think we're back in. Ashley's here. I'm drawing this 1687. I need a 30-degree angle here. Let me get my protractor. Do you guys have any questions for me while I'm drawing a 30-degree angle here? you got a question, just speak up. $30 is right there. Yep. Now, how long is it? Well, it'd be 10 centimeters long. Okay. So this is 0.5 centimeters. No, 0.5 meters. 0.4 meters. And one meter. And these are rods with smooth pins.
No.
Hey, we've got some people out there. We've got Jesus, Braxton, Ashley, Alex, and Taylor, and Stuart, and Ryan, and Mark. Got a good class. I guess we could write down the homework. You know what? Today's the last day of class. Did you guys know that? Went by in a hurry, didn't it? Here it is, the 2nd of December, last day of class. And according to what I've got written here, your final will be available December 7th, Pearl Harbor Day. When is December 7th? That's next Monday. So your final will be available Monday. December 7th, Pearl Harbor Day. And it will be due on the 11th, right? No. It will be due the 10th. Final is available next Monday. It's due on the 10th, which is, I think, a Thursday. Yeah, it's due on that Thursday. The last homework assignment is homework assignment 30. And it is, according to my meticulously kept records, are 19-3. Review problem 19-3. And it's due on the 5th. That's Saturday. What is that? Let me see what that problem is, just out of curiosity. R 19-3. I'm looking it up here. Well, I'm having a little trouble finding R19-3. There it is. It's on page 558. I got a bad feeling that maybe we've done that problem. And if you took notes, it sure would be easy for you to do that, wouldn't it? Seeing as how, if we've gone through it together, I don't remember, but I bet you can do it. So this is the very last homework assignment. Your final is available next Monday. Today's Wednesday. Does that make sense? Yeah, I think it does. It makes sense. Okay, and today we're talking about the ICZV thing. And I want you to understand it. So we're going to do problem 1687. And what do they want to know? Oh, I lost my place again. Let me look this up. They want to know. I didn't label all this stuff. This is D. This is C. There's smooth pins there. This is B. And this is A. And there's a 30-degree angle right here. 30-degree angle right there. There's the link, so we put those in there. Oh, this CD has got a angular velocity of 4 radians per second. 4 radians per second counterclockwise. And what do they want to know? They want to know the angular velocities of AB and CB. They want us to find the angular velocity of AB and the angular velocity of BC. That's what they want. Only they call it CB. Same thing, BC, CB, same thing. Okay, now how do you do it? Well, you know what ICZV stands for. Let me ask one of my excellent students. Let's go to Ashley. Ashley, what does ICZV stand for? Earth calling Ashley. Come in, Ashley. What does
Instantaneous center of zero velocity?
That's it. She's got it. That's it. And there's a method for finding it. I'll give you, I think it's about 3 steps. The first thing you do is you draw some velocities. I like to put my velocities in red. So let me write a little red V here. You put some velocities. Well, really, first thing you have to do is you have to identify the body that's in general motion. See, AB is in pure rotation. AB is in pure rotation. And you know what? CD is in pure rotation. See, they have a fixed pivot. And CD has a fixed pivot. And AB and CD are in pure rotation. It's BC that's in general motion. BC is in general motion. I think your book calls it combined motion. Because see, it not only has rotation, but it has translation. It's in general motion. And what you want to do is you want to put the little velocities on the BC. See, what we need here is the velocity of B and the velocity of C. Well, that's pretty easy to do. If AB is rotating in a big circle, here I'll kind of fake it. AB is rotating in a great big circle. There you go. I don't think it'll ever get over to here because it'll get stuck. But right at the moment, it's rotating in that circle. And the velocity of B is perpendicular. There it is. There's the velocity of B. That's your first step. And then the velocity of C. See, it's rotating in a circle too. Here, I'll draw you a circle there. There's a great big circle. Whoops, not that big. There's a big circle. CD is, at that instant, is spinning along that circle. Okay. I don't think it'll ever get down to here because it'll get stuck. But if you draw the velocity of C, it's going like this. There it is. So we did that. We drew the velocities. Now, the next step in the process is you have to draw perpendiculars to those velocities. Okay, well, we'll do that. Now, the perpendicular to that velocity there at B, well, it's going like that. Ta-da. Now, the perpendicular to this velocity at B, it's going like that. Come on now. There we go. Hey, look, they cross right here. Ta-da. That's step 3. You find the place where the perpendiculars cross. That's it. You see that point right there? That's the ICZV. Instantaneous center of zero velocity. Now what we got to find, we've got to find the distance from here to this velocity at B. Now how am I going to do that? Well, we got a little triangle down there, and we know the angle. We ought to be able to do it. Here, I'll draw it bigger for you so you can see it. See, there's a 0.4 meters, and there's a 30 degree angle, like that. See that little triangle right there? And then I need, see, here's your ICZV right here. I need this little distance right from here to here. See that little distance right there? Well, we could give it a name. If this is I and this is C, we could call this IC. What do you think? That's a nice name for it. Call it IC. Well, how long is it? Well, I think it's 0.4 meters times the tangent of 30. It's a trigonometry thing. You guys took you took trigonometry in school, so do that and tell me what it is. Go ahead. Fine. Gee, I can do it. No, I was going to say I can do that in my head, but I can't. Go ahead and find what that IC is. And I'm going to do it too. Now, if you don't understand that, I can go back and explain trigonometry to you with SOHCAHTOA. Just ask me and I'll go through it. Did you get IC is equal to 0.69282 meters? If you did, say, uh-huh. That can't be right. That's got to be wrong. Let me do it again. I did it wrong somehow. No. I'm glad nobody said uh-huh, because it's 0.23094. Now, if you got 0.23094 for IC, say uh-huh.
Yeah.
Yeah,
Uh-huh.
yeah, there's several of us. We're doing great. Now, I also need this distance here. If this is B and this is I, why don't we call this here BI? That's a nice name for it. Well, I could get that. I'll tell you how you could get that. You could go 0.4 squared plus 0.23094 squared, and then take the square root. Wouldn't that work? Yeah, I think it would. I think it would work. Yeah, okay, I'm going to do that now. Here goes. Okay, I'm thinking this BI here is 0.46188. Ta-da, we got that. Now, what is step 4? I showed you step 1, 2, 3. Step 4 is you use this equation. It goes like this. V equals R omega. You use it over and over and over again. And let me show you what I mean. Now, we've done all this before. This is a review. We're doing a review. But I don't want you guys to leave me and still be fuzzy about this. I want you to know how to do this. Okay. Now let's see. I just had a senior moment. What are we doing? Where are we? Who am I? What am I? And what are we doing? Let's see. Oh yeah, we're going to use this V equals R omega thing. Well, they told us that the angular velocity of CD was 4. Let me make some room here and I'll write that. You know about the final available the coming Monday. You know about there's one last homework assignment there. It should be on Blackboard. I need this room to write stuff. Need some room here. If you're wondering what we're doing, we're reviewing ICZV right now, and we're doing problem 1687 on page 370. That's what we're doing. Now, they said that CD is rotating with 4 radians per second. So the velocity of C should be equal to your 0.5 meters times 4 radians per second. I can do that in my head. I'm getting 2. A half of 4 is 2. I don't need a calculator to do that. I'm getting 2 meters a second is the velocity of C, and it's going to the left. It's going like that. But see, you can get the velocity of C another way. The velocity of C should equal to the angular velocity of BC times this distance from the ICZV, which is 0.23094 meters. And now we know this, we just figured it out, it's 2. And so the angular velocity of BC will be, plug that stuff in and we'll get it, go for it. We're going to find the angular velocity of BC. And let's see, 2 divided by 0.23094. Well, I'm getting an answer. I'm getting 8.66 radians per second. But now here's the problem. Is it clockwise or is it counterclockwise? Is BC clockwise or counterclockwise? Well, let me ask some of my students. We'll go to some of my students. Let's go to my friend Braxton. Braxton, unmute and say hello, please.
Hello.
Braxton, this is kind of messy, but there's a link here, BC. It's in general motion. Is it rotating counterclockwise or is it rotating clockwise? What do you think, Braxton?
I think it's clockwise.
You had a 50-50 chance to get that, Braxton, and you lost.
Oh.
Well, let's put it this way. I'm pretty sure it's counterclockwise. You still might be right. I wonder how I could convince Braxton of that. See, we know what CD is going to do. It's going counterclockwise. They told us that. And so I think what's going to happen, is there room for me to write it? Yeah, there's a little room over here. See, here's D. And you know that CD was here. I'll make it a little longer. And you know CD is going to rotate. So it's going to go like that. This will be the new position for CD. You guys understand that because it's rotating like that. Now, up here is this point A, and it's got to be connected to this C here. They're connected. B. No, wait a minute. No, that's all wrong. Just a minute now. No. A is over here someplace. That part is true. But we got a BC in the way. And I think BC is going to be kind of like this. And then here's AB. I think this is the before and the after. I know CD is going to go to the left. I know that. And what's BC going to do? Well, here's BC right here. I think it's going to kind of do that. I think it's going this way. I think BC is going counterclockwise. Now, Braxton said clockwise, but I don't think so. Did that make a lick of sense, Braxton?
Yeah, I guess I just thought since the velocity of B was going up, I thought AB would be up and kind of be the opposite of what you're saying.
Oh, I see what you're saying. Oh yeah, Braxton, what you thought made perfect sense because I drew this velocity of B going up, didn't I? Yeah, what you said made perfect sense, but you know what? I think I was wrong.
Okay.
I think the velocity of B is going down, not up. It didn't make any difference on our ICZV because when you draw these perpendiculars, they're the same whether, you understand? The velocity of B for definitely is either going down or it's going up. But when you draw the perpendicular to that, it comes out the same. Did that make any sense? Yeah, I can see what Braxton did, but I'm thinking now that this AB, it rotates clockwise. See the way I conned Braxton into this, I had him thinking that it's rotating up, but I don't think it is. I think it's doing this. Okay, now we got the angular velocity of BC. Now let's talk about the velocity of B. I need a little room here. I'm going to have to erase my wonderful drawing. I'm going to talk about the velocity of B. Now, the velocity of B should be the angular velocity of BC times this distance here now from the ICZV. We got that. That's the 0.46188. 0.46188 meters. And the thing is, we got the angular velocity of BC. Look, it's right here. Ta-da, and we got it. So solve for that. Find the velocity of B for me. Plug that in and get it for me. Here we go. Gee, I got a weird answer. Did you get 4 meters per second when I plugged that in? So we think the velocity of B is 4 meters a second. And the way I had it going up was wrong. I think it's going down. Okay, we got to use this equation one more time and we'll be through. Do you notice we just keep using it over and over and over? By the way, do you know where this equation comes from? Let me review that for you. It comes from this equation here. If you take the derivative of both sides, now r is a constant, what you'll get is the derivative of your arc length with respect to time equals that constant radius times d theta dt. And you know what this is? This is velocity. And this is angular velocity. That's where that equation comes from. It comes from this equation here, which has a name. It's a famous equation, and you all know the name of that equation. I can ask any one of you. We'll go to Jackson. Jackson, unmute and say hello, please.
Hello.
Yeah, hey, Jackson, this equation's an important one. What's the name of it?
I don't remember.
I love honesty. Jackson, I'll give you a hint. It starts off with the word arc. Arc. Do you need more help? Go for it, Jackson.
Is
What do you think?
arctangent?
Say that again, please.
Arctangent?
No, that's an intelligent one, but no, it's the arc length formula. Now, to be honest, Jackson, have you ever heard of it before? The arc length formula.
I've seen it. I just forgot what it's called.
Okay, well, that's fine. Now, I know you know this, Jackson. This theta, there's a catch. This theta has got to be measured in what, Jackson?
Radiance.
Yes, that's the catch. This has got to be measured in radians, or else it doesn't work. And if you take the derivative with respect to time, you come up with this equation here that we're just using over and over again, and we're almost through. We're almost through. I got some room right up here. We know the velocity of B, but see, the velocity of B should equal the omega of BC times this distance from the ICZV, which happens to be 0.4618 meters. And you know what the velocity of B is. We just figured it out. It's 4 meters per second. Now solve that, and get the angular velocity of, no, wait a minute. Yeah. No, we already did that. This is the one we know right here. What we're going to get is the velocity. Is that what they wanted? I don't know. Let me look and see what they wanted here. I'm mixed up right now. Let me see what they wanted us to find. If I determine the angular velocities of A, B, and CB. A, B, and C. Well, we already got CB. What about AB? Did we ever do it? AB. Oh, never mind. No, I think we need that. We need the velocity of B. Yeah, okay. We're on track. We're doing fine. We're going to get the velocity of B now. And it's going to be 8.66 times that, right? 8.66 times 0.46188. Well, we already did that. That's the velocity of B. It's 4. I don't know why I'm doing it again. The velocity of B is 4 meters a second. We've already done that. And if you want the angular velocity, see the velocity of B is equal to the angular velocity of AB times 1 meter. I can do that in my head. So 4 equals omega times 1. You know what? Omega AB has got to equal 4 radians per second. Okay, now here are the answers. We've got the omega of AB, and we've got the omega of BC. Now we're going to look up the answers in the back. This was problem 1687. Go to the back and help me find it. 1687. All right, I'm looking in the back here. 1687. They said the omega of BC is 8.66. The book agrees with us. And they said the omega of AB is 4 radians per second. The book agrees with us. Ta-da! We just completed problem 1687. Do you have any questions on that one? We're going to do another one, but do you have any questions on that one? Okay, well, let's do another one. We're going to do another ICZB, but I'm going to erase this unless you have a comment or question. Here's your chance. Go ahead, ask. All right, well, let me erase all this stuff, and we'll do another one. And the same, we're going to do the same rules here. We're going to find these velocities on the body that's in general motion. We'll draw perpendiculars. I'll try to draw the velocities the right direction, but the ICZV isn't going to matter. And then we're going to use this equation over and over again and get our answers. That's the plan. Okay. Now this problem here that I'm going to do with you, you're going to help me, is problem R16-4. It's a review problem. It's a review problem R16-4. Okay, well, let me find it. R16-4. Well, that's going to be at the end of chapter 16. Okay, there it is. I see it now. Okay, they've got a 45-degree angle there. 200 millimeters and 500 millimeters. Okay. Well, let me draw a 45-degree angle here. And I'll draw a 45-degree angle. Let me get my protractor here and draw a 45-degree angle. Here we go, 45 degrees, and puts me right there. There's 45 degrees. Now, how long is it? Well, it's supposed to be 200 millimeters. Nah, I think maybe I'm going to use inches this time. I'm going to go 2 inches. That's what I'm going to do. You can use any scale you want, but use a scale. Okay, here goes. There. I drew that. It's supposed to be 200 millimeters at 45 degrees. And then they have another one that's 500 millimeters, but it's at an angle of 30 degrees. Okay, I bet I can do that. Maybe. I don't know. A little bit scared about this. 30 degrees, huh? Okay, well, 30 degrees is right there. Okay. And how long is it supposed to be? Well, it'd be 5 inches on my scale. Okay, 5 inches. That puts me way down here. Yeah, I got 5 inches there. Well, this one here is, why don't I just call it 0.2? And call this one 0.5 meters. Yeah, that's good. We can label this stuff. AB. Yeah, there we go. AB. 0.2 meters. And then BC. Oh, there's a piston down here, you know it? And that piston is sliding on a surface. Come on now. The piston's sliding on a surface. See that piston there? Yeah. Okay. And that's C. A, B, C. There you go. And see, this is 45 degrees. I measured that. 45 degrees. And I don't know if you can tell it, but I measured that. That's 30 degrees right there. Okay, I've tried to do it to scale. And they said that AB has an angular velocity of 6 radians per second. You see this right here? It's rotating with an angular velocity of 6 radians per second. They want the velocity of that piston, or they call it a slider block. Okay. They want to know the velocity of the piston. All right, well, I erased my step-by-step procedure here, but remember your job is to find the body that's in general motion. Well, it's not the slider block, because the slider block is in pure translation. It's going in a straight line. The velocity of C is in a straight line. It's not rotating at all. Now, B here, it's got a velocity, a little bit hard for me to draw, but I'll try. It's got a velocity doing this. That's the velocity of B. That's point B right there. Okay, now according to our rules, our step-by-step foolproof plan, we now draw the perpendiculars to those. Okay, let's do that. Let's draw perpendiculars. Well, the perpendicular to this one is like so. There. That's perpendicular to the velocity of B. And the perpendicular to this one is like so. And point you, where they cross is your ICZV. Now what we've got to find is we got to find these angles. Well, if that's 30, I know what this angle is. This is 0.5 meters here. And this angle right here has got to be 60. Okay. And you know what? If that's 45 down there at that corner, this has got to be 45 degrees up in this corner. So you got a 60 and a 45. Now here's a little geometry problem for you. What's this angle here? I'm going to shut up for 30 seconds. And I want you to find that angle there for me. Go for it. I know you can do it. I'm not sure, but I'm thinking it's 75. Now let's check it. If you take 45, 75, and 60, they've got to add up to 180. Do they? Boy, you. I think they do. I think that's 75. So we've got that angle. Now I need some distances here. I need the distance from the ICZV down to the slider block. You want to call that distance maybe, I don't know, IC might be a nice name for it. We need that distance. Now we're going to need this distance here from the ICZV to point B. How about calling that maybe IB? That might be a nice name. Now I'm going to shut up here for about a minute and a half or so. And I want you to find those distances. We're going to need them in order to solve the problem. So go ahead. And then I'll call on some of my wonderful students to help us here. Find this distance IC. We know all the angles. Then find this distance IB. If you tuned in late, we're doing review problem 16.4. It's on page 406 in your book. That's what we're doing. And we're trying to find these two missing distances here. Well, I'll tell you what I got for this IC. Now I could be wrong, and if I am, I want you to help me. But I think it's 0.683 meters. If you got 0.683 meters, say, uh-huh. Man, I didn't hear a lot of uh-huhs. Now for this one here, this IB, I got 0.61237 meters. If you got 0.61237 meters for that IB, say uh-huh. Man, I didn't hear.
Yes, sir.
Hey, I heard one. Did anybody get this 0.683? Anybody?
Yeah.
Yes.
Oh, good. I bet we did it right. I bet we did it right. Now we're following this plan. And let me write out the plan one more time. First, really, step one, you really need to find the body that's in general motion. And in this case here, the body that's in general motion is this connecting rod BC, because AB is pure rotation and the slider block is pure translation. But BC has combined motion, translation, and rotation. Find that body. Then step number 2. Draw the velocity. In this case, you'd draw the velocity at B and the velocity at C. You draw those. That's step 2. Step 3, you draw the perpendiculars to those velocities. Well, I did that. Look, there's a perpendicular. There's a oh, look, they cross. In step 4, someplace they cross, and that is the ICZV. Step 5. Well, really, step 5, what you really need to do is find some distances from the ICZV. Yeah, there you go. In this case here, we find IB and IC. You need those distances because in step 6, you use this equation here, V equals R omega, and you do it over and over again. You might have to do it about 3 times before you get finished, and then you can find out anything you need to know. Okay, well, what do they want us to find out? Let me read this again. Oh, they want the velocity of the slider block. Okay. Well, I'll tell you where we are. I think we're right here. We've done all that. We just haven't written these equations yet, so here we go. Now, they gave us the angular velocity of AB, so the velocity of B, I can do that. The velocity of B is going to be 0.2 meters times 6 radians per second. I can do that in my head. I think it's 1.2 meters a second. And I even know the direction, it's kind of doing something like that. See it there? Velocity of B. Great. Now that velocity of B can be written another way. It can be written as the angular velocity of BC, which we don't know, times this distance, 0.61237 meters. See, every point on this BC has the same angular velocity. It's sort of like if I spin myself in a circle, my ears have the same angular velocity as my nose, as my fingertips, unless I'm waving my arms. If I keep all my arms still and I don't turn my head around, my angular velocity of every part of me will be the same, and every point on this BC has the same angular velocity. Okay, now we know we know what this is. We just got it. It's 1.2, so we can solve for the angular velocity of BC. Okay, do that with me and check me now. Make sure we get this right. Did you get 1.959 something radians per second for the angular velocity of BC? Okay, then what? Hey, then we're almost finished. Then we're going to use this same doggone equation again, and we're going to find the velocity of the slider block. It's going to be the angular velocity of BC times the 0.683 meters. Hope you can read my writing. Okay, here we go. We know what this is. We just got it. It's right here. Times 0.683, and I'm getting the velocity of C. The slider block is 1.338 meters a second. Okay, now let's see how we did. This was review problem 16.4. And I'm going to look back here and see what they said the answer was. Review problem 16.4. Okay, we're digging around in here. Review problem 16.4. Here's what they said. They said the velocity of C, this is in the answer book, is 1.34 meters per second. Hey, I think we did okay. Look, if you rounded this off, you'd get 1.34, wouldn't you? They just rounded off. They have another answer. They say omega is 1.96. Now, what omega is that? 1.96 radians per second. Did we get anything like that? What are they talking about? Oh, look, that's this one here. This is the angular velocity of BC, only they round it off. If you round that off, you get 1.96. See it? We got 1.9596. I think we did good. Is there any question on the ICZV? Well, let's move on. We have one more topic to discuss today. Unless you have a question or a comment, I'm going to erase all this wonderful stuff. Okay, nobody said anything, so I'm going to erase all this. I want to talk to you now about relative motion. We'll see if we can do a relative motion problem. Now, we've studied this. I just don't have that warm, fuzzy feeling about it that you guys got it. You know about relative motion. It's kind of like if two airplanes are approaching each other, artist rendition here. Here's an airplane. And here's a pretty pathetic looking airplane. And here's another one here. here. And if this one's approaching at 500 miles an hour, and this one's approaching head on at 500 miles an hour, you know what the relative motion is? It's 1,000 miles per hour, isn't it? See, if you're in one of those airplanes, you're sitting here in this airplane, you're looking out the window and you see this other airplane coming at you. First thing you see is just a speck. And that speck starts to get bigger and it gets bigger and it gets real big, and it's time to get the heck out of Dodge. I would maybe turn and dive or get the heck out of there, because he appears to be coming at you at 1,000 miles an hour. Relative motion. Okay, we're going to do a relative motion problem. This is problem 1695. It's on page 271. So see if you can find it. 1695. This is going way back. We studied this a long time ago, but I'm just not convinced we know how to do it. So we'll find out. 271, okay. That's the wrong page number. Just a minute now. 16. Well, help me find 1695. That's the wrong page number. But we'll find it here. Yeah, it's 371. That's the problem. It's on page 371. And they have a car that's going 80 feet per second. You know, that's really not very fast. Let me tell you how fast that is. 80 feet per second. 60 miles per hour is 88 feet per second. So 80 feet per second is 54.5. You're not going that fast. 55 mile an hour, puttering along there. It's on a wet road, but it's a rear wheel drive. It's not front wheel drive, it's rear wheel drive. See it? But the rear wheels are slipping. She's got the accelerator on. And she would be laying rubber. The only thing is the road's so slick that she's not laying any rubber, but the back wheels are slipping. Let me just draw you a picture of the back wheel, okay? Here's your back wheel. And this wheel is spinning. They said, if you read it here, I'm doing problem 1695. It's on page 371. And they said it's got an angular velocity of 100 radians per second. Okay. They want to know the speeds of point A, B, and C caused by the motion. Now you got to understand that the axle of that wheel is attached to the car, and it's got a velocity. It has a velocity of 80 feet per second, which we figured out was about 54 miles per hour, but we didn't need to know that. That was just kind of entertaining. Now here's what they want to know. you've got these different points here. You've got a point A, and you have a point B, and you have a point C. They want to know the velocity. Let me read this. Determine the speeds of A, B, C. Yeah. They want to know the velocity of A, B, and C. Okay. Well, let's see what we can do. We'll do A first. We're going to try to find the velocity of A. Well, we've got an equation for relative motion. It's the relative motion equation, and it goes like this. See, this is the center of the wheel. We'll call it the center of gravity of the wheel. And our equation goes like this. The velocity of A relative to G is equal to the velocity of A minus the velocity of G. Now see, I know the velocity of G. It's 80. It's 80 going to the left. I know that. That's the velocity of the center of the wheel. We can also get the velocity of A relative to G from this equation here. The velocity of A relative to G is equal to R omega. So it's like you're just spinning, and that's all you're doing. And the R is, well, I don't know. Let's see what the R is. It's 1.4 feet. This distance here is 1.4 feet. So this is 1.4 feet times 100. Hey, I can do that in my head. I'm getting 140 feet per second. That's the velocity of A relative to G. Hey, we just solved that. Ta-da! We did great. We got the amount. But what about the direction? Well, the direction, if it's spinning that way, is like that. So that's like that. It's 140 going to the right, right? Yeah, yeah. Okay, now we have an equation here, and we're going to solve it, and we're going to find the velocity of A. That's what they wanted. Now, whenever you solve these are vector equations, guys. These are vectors. Put a little vector notation there. You have to decide on your directions. Why don't we just say going to the right is your positive x-axis? That'd work. So if this is going to the right, it's a positive 140. There's your equal sign. There's your unknown that we're going to solve for. There's a minus sign from the equation now. And now this velocity here is 80, but it's going to the left. That's a negative 80. Do you understand? If going to the right is positive and this is going to the left, then that's a negative 80. That minus sign comes from the equation. This is the definition, really, of relative motion. We could put 3 lines there. This is the defining equation for relative motion. Okay, well, we got an equation now. We can solve this. Let me get this kind of out of the way here. Okay, well, let's see. That makes that a plus. 2 negatives make a plus. But you'd have to subtract it over here, wouldn't you? To do the algebra. 160? Or no, 60? Are you getting a velocity of A is equal to 60 feet per second? And since it's plus, it's going to the right. That's what I'm getting. I'm getting the velocity of A is 60 going to the right. So here's our answer. Velocity of A is 60 going to the right. I wonder if that's right. Well, we'll look up the answers here in a little bit. I bet it is. Okay, well, let's do the next one. We did that. They want to do B now. Let's do B. Okay. Maybe we should look up that answer before we forget. Go to the back. This is problem 1695, and we'll see if we got that right. 1695. Now they say, hey, that's exactly what they have. They have 60 feet per second going to the right. Yay, we'll put a little happy face on that. So we got that right. Okay, now let's do B. Was there any question on that? All right, let's do B then. I need some room here someplace. Well, why don't we just leave that equation up there? That's a nice equation, but see, now we're going to try to find the velocity of B relative to G, and that's going to be the velocity of B minus the velocity of G by definition, and we're going to try to find the velocity of B. Okay, make some room here. Now, the velocity of B relative to G, you know what, that's straight up. And it's equal to 140. I think it's 140 feet per second. It's the same deal here. It's B relative to G is the 1.4 times 100. You get 140. But see, B relative to G, you're spinning, you're going straight up. So we got that. Equals the velocity of B minus the velocity of G. Well, the velocity of G is a negative 80. Didn't they say that? Negative 80? I erased it here. I think that's what they said. Yeah, negative 80, yeah. Yeah, that's it. Well, it's going to the left, and we said going to the right is plus. Well, no, wait a minute. I'm getting mixed up now. We got two different directions here. These are not all in the same direction. Why don't we do this? Why don't we have this be the positive y-axis, and this could be the positive x-axis. So the velocity of B relative to G, you know what that is? That's 140 J. We'll have a little J vector going that way, and we'll have an I vector going this way, is equal to the velocity of B. Now that's a plus. And here's where I'm getting mixed up, guys. Sorry. We've got the velocity of B minus the velocity of G. Well, the velocity of G is minus 80I, isn't it? Yeah, it's minus 80I. So what you have here is the velocity of B plus 80I. Now we're going to solve this, and we'll get the velocity of B. This one's a little trickier. Velocity of B is negative 80I plus 140J. Just doing the algebra here. Why don't we draw that? You know what that is? That's a negative 80 and a positive 140. And this right here is the velocity of B. And it's equal to, well, you'd have to square it. Take 140 squared plus 80 squared square root. Let's do that. We'll get the velocity of B. It's a little bit tricky. I'm getting the velocity of B, got lost here, is 161.2 feet per second. And you could even get the angle here. We could find this angle. Now that angle is the arctangent of 140 over 80, right? Take 140 over 80, arctangent, it's 60.2 degrees. So this should be our answer. This should be the answer in the back of the book for the velocity of point B. Now let's go back there and look. This was problem 1695. I think I got lost. Here we go, 1695. It says the velocity of B is 161 feet per second at 60.3 degrees. I think we did pretty good. They said, the book says 161 feet per second at an angle of 60.3 degrees, and they draw it. It's kind of like that. Let's don't cry over it. The 0.3, the 0.2, I don't know. Maybe we rounded off, maybe they rounded off, I don't know. But we really did good. Now let's do point C, and we'll be done with this relative motion problem. That one was a tad tricky. Do you have any questions so far? We're studying relative motion now. This is our basic equation here, only we're not doing A or B anymore. We're going to do C. We're going to put C in here. That's the plan. I need this space to write stuff. But we can do it. Relative motion. What's tricky here is this stuff is in 2 dimensions. Of course, we live in 3 dimensions, don't we? All right, we're going to do C now. Now, the velocity of C relative to G, it's just going this way. And didn't we say that's 140 feet per second? I erased it, but I think that's what we had. So this is 140 feet per second, and it's going to the left. And there's an equal sign. And see, we don't know what the velocity of C is. We're trying to find out. But the velocity of G is 80. That 140 someplace else. It's but it's going to the left. It's 80 going to the left. We got to decide on our directions. Why don't we just say going to the left is the positive direction? Then you can just leave that, and you leave it like that, and you're done. Solve this for VC, and what you'll get is, looks like 220. What's 80 plus 140? 220, I think. It's 220 feet per second going to the left. Okay, let's look up the answer book. The velocity of C, go in the back. We're looking up the velocity of C for problem 1695, and they said 220 feet per second going to the left. Hey, we got what the book got, exactly what they got, and we've worked some relative motion problems. Okay, well, let's see. We've had a review of ICZV and relative motion. Do you have any questions? Well, okay, do your homework. Do that test whenever I told you it was going to be available. Turn it in before the due date on Blackboard. And it's been a pleasure. And I will see you around, okay? Any last comments?
Thank you very much.
Well, bye-bye for now.
But
Bye.
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 Thank you.
Thank you.